Hi, everyone, and welcome back. We are going to go ahead and continue our lectures with statics and torque. Oops, there we go. So our first question is going to be, what is statics? And statics is essentially the study of forces in equilibrium. Okay, and before I had talked about equilibrium as just being basically that there is no external force, or the external force is zero on the system. But in order for it to be in true equilibrium, we have to have another condition, and that is going to be about torque. Okay, so we have two conditions here. So again, the net external force must be zero, but also the net external torque on a system must also be zero. Okay, so we're going to go into depth of torque today, going into further depth. Okay, so again, looking at equilibrium, two main types. That's going to be static or motionless equilibrium, and dynamic equilibrium, or an equilibrium that has constant velocity. Okay, so this first example here, we have this guy just standing there. He's not moving. Okay, and there is a weight that he is applying to the ground due to gravity, and the ground is also applying a normal force, okay, in the complete opposite direction. And so our net force on this body, on this stationary person, is zero. Okay, so this is called static equilibrium. Okay, now we have another one called dynamic equilibrium. So take this car here. Okay, it is moving with a constant velocity in this this direction. Okay, and we have because it is moving, we have an applied force in that same direction. Okay, we have the weight of the car being pulled down due to gravity. Okay, and then we have all of our normal forces on the tires and wheels. Okay, and a frictional force in the opposite direction of the applied force. Okay, so our free body diagram would look like this. Okay, so we have all of these normal forces adding up to be the exact opposite of our weight here. Okay, and our applied force is going to be the same as our frictional force. Okay, because it has a constant velocity. And so we have that the net force is equal to zero. Okay, so again, this is the dynamic equilibrium. Okay. All right, so again, we want to look at equilibrium versus non-equilibrium. Okay, so equilibrium here, we had that there was a moving body and there was a stationary body. Okay, so if we have a basic idea of equilibrium, we would think of it as this body remains stationary, right? So here we have a hockey stick, and there is two forces being applied to the hockey stick at the same point here, right? Basically along this axis here. Okay, it's being applied at the same place in opposite directions. And so our net force is zero here. Okay, but what if we're looking at where we do have the same amount of force, but now at different points of this hockey stick? Okay, so we have this point here that it's being applied, and then this force here, or this point here. Okay, so we have two different points. Technically, the free body diagram would look like this. Okay, so the net force is zero, but as maybe you guys have done before or think about, say that we have this pin, okay, and I apply a force in this direction, right? So in this direction, and then another one in this direction. Okay, so again, it's very similar to this case that we have here with this hockey stick, but now I'm just looking at a pin. If I do that, this pin is going to rotate, right? It's kind of hard to do in midair, but you see what I mean, right? So I've got a force being applied up here, a force being applied up here. It can be the same force, but it will rotate, okay? So this tells us that we are not in equilibrium, okay? We can't just say that because we have a net force equals 0, that our system is in equilibrium. We have to have that torque aspect, and that has to do with rotation. Okay, so let's go ahead and start talking about torque. So that is going to be something that's like the rotational equivalence of a force, okay, like I was just talking about here. And it's the measure of effectiveness of a force in changing or accelerating a rotation or changing the angular velocity over a period of time. Okay, so again, we have, say we have A here, excuse me, and we have this hockey stick, and we have a force being applied in this direction, and if it's nailed down, like it has here, or this could be also called its pivot point. That's another term for it here. Okay, that's its pivot point. If we apply a force, it's going to rotate along that pivot point, right? So again, taking my pin as an example, if I keep this hand stationary, okay, and apply a force here, it's going to rotate just like that. Okay, again, this would be my pivot point here, and then if I push on it with some force, it will rotate in that direction. Okay, so this is what we mean by torque. Okay, so let's go ahead and quantitatively look at this. So look at the numbers and equations and such. Okay, so this is the equation for torque here, where tau, this Greek letter, you can just draw it like that. Okay, that is your torque. Okay, your R is your radius. Okay, so this would be from your pivot point to where the force is being applied. Okay, so that would be your R. So again, R is from pivot point to the force vector, I should say. Okay, or where the force is being applied. Okay, so it's going to be that straight distance. F is, of course, your force, and then this sine theta, the theta is going to be your angle between your force vector and your radius here. Okay, so theta between force vector and your radial vector R here. Okay, so this is going to describe your torque. And as you can see, this is going to have the SI units Newton meters, or newtons times meters. Okay. There is an alternative form that we can put this into if we want to describe another term here, and that's going to be the perpendicular lever arm. Okay. And that is just going to be your R sine theta. Okay. And in this case, in part A, or in figure A, that is going to be this here, this perpendicular R perpendicular. It's going to be your lever arm. Okay? So it's going to be like opposite your theta. Okay, so that is just another form, but we just know that we want, so I guess I should say that if a question is asking for the perpendicular lever arm to solve for it, you can just use that equation right there. Okay, just remember that it's r sine theta. Okay. Now in B here, just to give you guys another example, if we have a nail here at point B, oops, and we have a force that's being applied at the same point, okay, now our rotation is going to be in the opposite direction, okay, and our perpendicular, or our lever arm, okay, is actually the same as r here, right? Okay, it's going to be very, actually, whoops, let me erase that. Erase. Whoops, I didn't mean to do that, but okay. I guess what I mean to say, your R lever arm is the distance between this point, this pivot point, and your force here. So in this example here, remember that our R is from our pivot point to our force. Here we should have the same thing, okay, from our pivot point to our force where it's hitting the hockey stick, okay? So in the middle there is where, whoops, we should have what R is. So that, oh, that's terrible color. Our R should be that leg there of the triangle. Pin gray. R, okay? But here we don't have an angle to describe that, but it's just trying to get you to understand the lever arm, okay? So let's go ahead and move on here with talking about equilibrium, where both conditions are satisfied. Okay, so this is an example that the textbook has, and we have two kids, kid 1 and kid 2, okay? This one has a mass M1 that is less than the mass of the second kid, M2, okay? And so for them to sit on this seesaw and not be moving, okay, they have to sit at this certain point, okay? They need to increase their distance from the middle in order, or one of them will need to shift their distance from the middle point here, this midpoint, in order for them to be in equilibrium. And that's what they've done. So if we increase our R1 for this smaller kid, that means more of the, how should I say, this force will increase, and so then it would be equal to this force over here. So it's like a balancing act, right? So they need to sit, the lighter kid needs to sit further from the pivot point. The heavier kid will need to sit closer to the pivot point, okay? So this is something that we can also think about when we are, say, let's see, if we're trying to, say, lift something heavy, okay, and instead of, you know, just straight picking it up, sometimes we can use a system like this. Okay, so if there is a person who is trying to lift up a rock, say, and he's got something like this, like a plank of wood, if he is at some distance, he'll be able to use this pivot point and lift that rock by pushing down here. So it's something that we can use and see in everyday life. If you're interested, you can look into that a little more. Okay, so let me go to OneNote for an example. Okay, whoops. Okay, so here is my example. Now we are looking at those two children that we were just looking at. Okay, they're balanced on a seesaw. Whoops, I did not mean to do that. They're balanced on a seesaw of negligible mass, just like we were looking at. Okay, and the first child has this mass of 26 kilograms. So I'm going to say M1 equals 26 kilograms and sits at this distance, R1, 1.60 meters from the pivot point. Okay, so if the child, the second child, has a mass M2 of 32 kilograms, okay, how far is she from the pivot point? So we want to know what R2 is. Okay, so go ahead and pause this and maybe start thinking about what we can do to solve this problem. Okay, so remember that we are looking at this situation here. Okay, so let me go ahead and put that into frame. Let's see. Okay, so remember that it says that they are at equilibrium. Okay, so they are balancing. Okay, and we, I can go ahead and get started here. We remember that torque, okay, from our equation here, whoops, is equal to R times our F times sine theta. Okay, so let's go back. And we want to figure out what our torque is in this situation. Okay, so we've got three different torques going on. We have torques due to this mass, due to this mass, and then due to this mass. So it did say, it did say that we are going to ignore the mass of the seesaw. Okay, so we can call that T of the pivot point. We're going to ignore the mass, so we're not worried about any kind of like force due to gravity here, okay? And our R, or our radius, if we call this 0, okay, which we can, right? Then our R would be at 0 meters, okay? And then we'd have some F sub P, and so that just tells us 0 Newton meters of torque at the pivot point. Okay, so we can just kind of ignore that piece there. Okay, so if we want to know the torque of the first one and the torque of the second one, we need to identify these things, right? So let's see. For T or tau 1, we can say that, let's see, or whoops, did not mean to do that. Our R1, okay, times our F, and our force in this case is going to be our weight here. So weight of the first kid, okay, and then times sine of our theta. So what is our theta going to be? So remember, from here, our theta is between our r and our force, okay? Our radial vector and our force vector. So let's go back. Our force is pointing straight down. Our radial vector is this way, so it would be 90 degrees, right? So it should be 90 degrees. Okay. Now for the second one, we have R2, which is what we're looking for, times our weight of the second one. And if we claimed that this way is positive, okay, so then we would need to say this way is positive. I know that was a little confusing. Let me try to draw on it. Let me see if I can do that. Draw. Oops. Okay, so again, in these red, I said that this way, which is clockwise, so clockwise is positive. That means if I want to know the angle between R2 and W2, and that would be this way, that way is actually negative. Okay, so we can go all the way around to get whatever that would be. That would be either you can say sine of, I think it would be 270, or you could just say negative 90 degrees. Okay, whichever one works for you. So again, I claimed that clockwise was going to be positive, so then my counterclockwise motion would have to be negative degrees. Okay, so let me double check that that was correct. Yes, okay. Okay, I just wanted to make sure that that 270 was correct. Okay, so now we have a couple of things here. Okay, we know our tau 1, our tau 2. Now it states that they are in equilibrium. So equilibrium, remember, states that our tau, our net tau equals 0. Or tau 1 plus tau 2 must equal 0. Plus the pivot point tau, but we're not worried about it in this case, okay? So that tells me tau 1 should equal a minus tau 2. Okay? All right, so using that information, okay, we can solve this now. So let me go ahead and move over here real quick. So tau 1 is R1 times our weight of 1. And remember that weight is just mass times acceleration due to gravity, okay? So we have m1 times g sine 90 degrees equals negative R2 m2 g times sine, I'm going to put negative 90 degrees. Okay. Now, sine of 90 is just equal to positive 1. Sine of negative 90 is equal to negative 1. Okay, so we can now plug our values in. Okay, so R1 is 1.6 meters. M1 is 26 kilograms. Okay, we have G on both sides, so those can cancel. Okay, and that's just times 1 equals R2, which is what we're looking for, times M2, which is 32 kilograms, okay? And our negative times our -1 over here is just going to be +1, okay? So now we can solve for our R2. So 1.6 times 26 divided by 32, and we get the radius is 1.30 meters. Okay, so that is our radius at where our second child will sit to be at equilibrium. Okay, so that was part A. Let's see, now we are looking at part B. What is F sub P, the supporting force exerted by the pivot? Okay, what is the supporting force exerted by the pivot? Okay, so what we will need to do is maybe draw this out in a simple way real quick. So remember that we have this idea, okay, FP, which is what we're looking for. We have some weight here and a weight here. Oops. Okay. And we know that since it's at equilibrium, there should be an F, or a net force, that equals 0. Okay, so we're going to go off of this idea in order to solve for our pivot point force. Okay. Looking at this, we know that our forces are all in our y direction, so we can ignore our x direction. So it's really net force in the y direction equals 0. Okay, so let's go ahead and write this out. Okay, so we're just using the same kind of stuff that we used to use looking at forces. So we have FP minus W1, since it's in the negative y direction, minus W2, again, minus direction, or negative direction, equals 0. Whoops. Equals 0. Okay, so we can solve for this. FP equals W1 plus W2, okay, which is just the first mass times gravity plus the second mass times gravity, or gravity times mass 1 plus mass 2, whichever way you want to do it. Okay. So that's going to be 9.8 meters per second squared times my mass of the first one, which is 26 kilograms, plus my second mass, which is 32 kilograms. And then you obtain, let's see, 26 plus 32 times 9.8, and we get 568 newtons. Okay. All right, so that is going to be your force that's exerted by the pivot. Okay. All right, so let's go ahead and go back to our PowerPoint and continue the lecture. Oops, there we go. Nope, wrong button. There we go. Okay, one last thing that we need to talk about is going to be stability. Okay, so this is going to have to do with how stable an equilibrium is. Okay, and I have a couple, or 3 different types here. Okay, so we have a stable equilibrium. We have, we have a stable equilibrium, we have an unstable equilibrium, and we have a neutral equilibrium. Okay, let's start with the stable one. So that is going to be the idea that when an object is placed or displaced from equilibrium, okay, it experiences a net force or torque in a direction that's opposite of the direction of displacement. Okay, so take this one for example. Oh shoot. Why doesn't it want to keep the pin on? Okay, so take this one for example. This is going to be your stable type. You have a pencil that is clearly perfectly cut, okay, and it has been moved or displaced in this direction. So that's your displacement, okay? And it is now sitting at some pivot point here, okay? And so this, after you let it go, it'll move back this direction. Okay, so it's going to be moving in the opposite direction of your displacement. Okay, so think about if you hold, I don't know, maybe like a cup or something, and just kind of tip it like this in that direction, just a little bit though. So not too far to overpass the center of gravity, or else it might topple over. Okay, but if you're just moving it just a little bit, it'll exert some force to kind of come back. Okay, so this is going to be a stable equilibrium. Okay, now we have another kind called an unstable equilibrium. Okay, and that is going to be where you have a pivot point, such as this one. Okay, and when it is displaced, okay, so again, excuse me, when we have some displacement vector, like so, okay, it experiences a net force or torque in the same direction. So then we've got some kind of torque or something moving in that same direction as the displacement. And so then it will eventually topple over. Okay. Then we have the third, where its equilibrium is independent of any displacements from its original position. Okay. So excuse me. Its equilibrium is independent of displacements from its original position. That is a neutral equilibrium. So here we have an example of one, okay, where we've got some type of sphere or circle, okay, and as it rolls in either direction, so if I put some displacement vector here, okay, and it rolls, the equilibrium is going to be independent of that. Okay, so it's always going to have its little pivot points as it goes around. So this is neutral. This one is a little bit, I would say a little bit more, I would say confusing than either the stable or unstable, but maybe finding some other resources out there, maybe like Khan Academy, maybe they have something on there about it. But the main idea is knowing the difference between stable and unstable equilibriums. Okay, so now let's go ahead and in the next video, we're going to do some examples.